speaker is Xinshuo Weng. I hope I'm pronouncing it right. She's a PhD candidate at Robotics Institute of CMU, advised by Chris Kitani. She received her master's degree at CMU, where she worked with Yasser Sheikh and Chris Kitani. Prior to CMU, she has worked at Facebook Reality Lab as a research engineer, building photorealistic telepresence. She finished her bachelor's from the Wuhan University, and her core interests lie in 3D computer vision, graph neural networks for autonomous systems. She's developed the famous AB3D MOT multi-object tracking system that received greater than 1,000 stars on GitHub. Uh, she's leading she's leading a few autonomous driving workshops this year at NeurIPS 2020 and HKI 2021, as well as ICCVIT 2021 and IROS 2021. She's been awarded the Qualcomm Innovation Fellowship for 2020 and Facebook Fellowship finalist for 2021. So Xinshuo, if you're around, please, you can take the floor.
Yeah, thanks, Ravi. Thanks for the invitation. Let me start screen sharing. Oh, wait. Can you see my slides?
Yes, perfect.
Okay, cool. Okay, yeah, thanks for the invitation again. Let me just jump right into it. So today I'm going to present Pointcloud forecasting for autonomous driving, approach, benchmark, and the challenge. Okay, so let's get started. So as we all know, perception and prediction are important components in the autonomous driving stack. And there are many popular or standard pipelines. So one of them, I believe everyone knows here, is that you have these sequential detection, tracking, and forecasting pipeline given the sensor data. And then once you have the trajectory forecasting result or the prediction results for the surrounding road participants, you can feed that information to your planner to tell the Eagle vehicle where to go, right? So that's one of the standard pipeline. And let's just go a little bit more details to understand this, and we will use in the following talk. So first of all, for the standard data, there are different kind of sources you can use, but the LiDAR and RGB are the most commonly used ones. And once you have the standard data, you fit into detector that give you these kind of 3D bounding boxes, right? So those represent the XYZ location of the object in 3D world and how their orientations are, and also the shapes of these objects. And then you want to associate these objects across time, not just detections at each individual frames. So then you can get trajectories, right? Because the detections boxes are associated through time. With these trajectories up to the current frame, you can do a prediction, which is basically what this trajectory forecasting algorithm or modules means. You kind of predict probabilistic trajectories for each objects, then where they will move and what's the probability of that trajectory is. Okay, so that's the standard pipeline. And we've seen a lot of progress in these kind of pipeline or each individual of this pipeline, individual module of this pipeline. For example, you see like hundreds of papers in detector every year, and also tracking prediction. A lot of progress using newer model like transformer or graph networks and etc. But the overall pipeline of these detection, tracking, forecasting stacks always kind of stays the same. I mean, there are other kind of pipeline. For example, you can do end-to-end from sensor data to planner directly, but these kind of interpret or intermediate modules inside the autonomous stack kind of remains the same. You always follow the detection, tracking, and forecasting, rather than like inverse order or different kind of combination of the orders, right? So in this talk, we are kind of trying to explore in this direction by posting the question of, is this really the best place, the last module here in this pipeline, the best place to perform prediction or forecasting, right? So there are other works that try to do forecasting for kind of video prediction, right? So we're kind of inspired by that line of work. Like, can we do prediction or forecasting upfront and use that information for downstream detection and tracking modules? So that's kind of the idea. Can we do prediction right after the sensor data? And the answer is yes, because we have seen a lot of success in other domains. So we're kind of proposing a forecast and detect pipeline that inverts the order of forecasting. So here again, it's showing the standard pipeline where you have the sensor data. Here we're showing the point cloud in the bottom left. And then you could do detection and tracking, get trajectories, and then forecasting into the future, right? And then what's the difference of this pipeline to our proposed forecast then detect pipeline is we're kind of doing this forecasting up front for predicting future point clouds, right? So this is illustrated in here. You kind of forecast where all the points are gonna move in the 3D space, and once you forecast that sensor data into future, you can do downstream detection tracking that give you directly the trajectories in the future, right? Not trajectory up to the current frame. So okay, so the difference, you move forecasting up front, and then we are forecasting the sensor data, not object positions. Okay, sounds right. To give you a quick sense of what or how good we're doing in this kind of new direction, here is a video demo. I hope the online streaming video quality is okay. So as you see here, the point clouds in this video are the point cloud generated by our point cloud forecasting algorithms. They look a little bit dirty, but the boxes you see on this point cloud are the results from the downstream module, basically the detector and tracker. Right? You see those boxes are actually tracked very well. The identity across time is kind of consistent, and also the location of the box looks kind of reasonable. We will show more detailed demo later, but this kind of demo give you a sense that these types of pipeline, this SPF square pipeline, which we call it, the longer name is sequential point cloud forecasting for sequential post forecasting. So that's what we call it, SPF square. So yeah, so the predicted point cloud preserve object information so that you can run this downstream detector and tracker to get the boxes you want. And the result is equivalent to the standard pipeline, the standard detection, tracking, and forecasting pipeline, right? Because at the end of the day, you're getting these object trajectories in the future. Okay, so we kind of briefly discussed this new pipeline. So what the advantages of this pipeline, or where are we going to do this, right? So the first and the most obvious one is that this kind of thing, this kind of new pipeline does not require human annotation for forecasting, right? Basically the point cloud forecasting part. If you think about it, this is same as the video prediction task or the algorithms people have developed. You're just giving the sensor data in the past and forecast the sensor data in the future. So there isn't a need to kind of draw some boxes or masks by humans in order to train your model, right? So and we also know that the point cloud data is prevalent nowadays, right? So you see all of these autonomous driving data sets, they all have point cloud data, like Waymo, like Kitty, NewsInst, and etc. So we can kind of leverage those large-scale point cloud data that already exist. And all of these kind of benefits come from this task, like we just discussed, this sequential point cloud forecasting, right? Because this task doesn't need any human annotation in order to train and evaluate it. Okay. So with this advantage, we kind of do tiny experiments here by showing how the performance can scale with more point cloud data, since we have a lot, right? So here we draw two figures where the y-axis are showing error. We kind of have two different errors here. One is chamber distance and Earth mover's distance, and axis is the amount of training data you use. And both, like all of these data points are evaluated on the same test set. Basically, we're using the same amount of test set to kind of evaluate the performance, but you get more and more training data from the left to the right in x-axis. So basically, the figures tells you that if you have more data, performance kind of improve because the error, you see error goes down. So that's normal, and we can kind of leverage this performance scaling from a lot of point cloud data we have in the modern driving data sets. Okay, that's good. Yeah, so now let's just jump a little bit into these new tasks, sequential point cloud forecasting, because I guess there are still a lot of people don't know this task, and we're trying to advocate this new task to the community. So basically, the goal is that we are given a sequence of past point clouds, and we're trying to predict the future of the point clouds, right? And this kind of sounds straightforward and simple to understand. But there are kind of two key differences compared to the existing task. For example, the one we're kind of compare here is the trajectory forecasting, where you only want to forecast the foreground objects, right? You don't care about anything in the background, or you hope that anything in the background, like any obstacles or anything that can affect the movement of objects, can be implicitly learned in your algorithm, but you don't kind of explicitly predict for them. But in the point cloud forecasting task we're proposing here, you're basically forecasting everything. You're explicitly predicting everything in the 3D world, which is kind of more challenging, but we are hoping to get more information out of it. And the other thing is that it's more challenging compared to similar point cloud reconstruction task. So if you think about this point cloud forecasting, it's essentially a point cloud generation task as well, but you're generating a sequence of point cloud rather than like many pair work are doing single frame point cloud generation or on the indoor objects, right? For example, decks, chairs, and etc. But here we're generating for outdoor scenes. So as a result, you kind of get a lot of or larger scale of the point cloud data to process, because you're dealing with a sequence and also you're having a large scale point cloud. Normally, for example, if you get data from Velodyne 64, you're having like 1.5 million over 10 frames, for example. So that's pretty large. So it's challenging to process and kind of design your algorithm to take care of every details inside the data. Okay. So how are we going to solve this problem? Or the other question we can ask is how to learn representation from these large scale point cloud sequences, right? So in the paper we kind of published last year, we're developing a very simple algorithm to this. The reason that we want to make it simple is that first it's a baseline, and second is that we want to compress the data so that the model can kind of fit into the memory, right? Because we have large scale data to process. So basically, we're using a fully connected LSTM, or many people know it as 1D LSTM, right? So you only have one-dimensional feature in your LSTM hidden state. So in order to do it, we first just pass through the point cloud data at each individual pass frame to a frame-wise point cloud encoder, right? So you can either use PointNet, PointNet++, or any point cloud-based encoder you prefer, or any range-based encoder you prefer, but you have to convert the point cloud into range image first, right? So anything you prefer, you can use it here. And after that, you can get some one-dimensional feature. You pass through into your LSTM model. Sorry. So that will give you the hidden state in the next frame after temporal propagation, right? And then you do some decoding, which is similar to the encoder, but you're doing it in the inverse way. For example, you can also use PointNet++ and the range-based method to generate the point clouds. And afterwards, you just compute the loss and train your network, which you can use temporary distance, for example. So it's a pretty simple solution, and then we kind of get in reasonable results out of this. So here you again we see some video demo from this simple baseline. On the top, for the red point cloud demo, here is from the ground truth or the real world data that you capture using LiDAR sensor, and on the bottom you see the point cloud prediction result from our algorithm, right? So you see all of these kind of blobs showing in the bottom video, which is essentially the objects that the algorithm predict, or they believe the algorithm believe the objects are existing in the future LiDAR data, right? So they kind of match with the ground truth to some extent. So that's why we think is kind of decent as a baseline method. But something kind of bad is that the background, or the like you see these kind of walls and some traffic cones and etc. Those things are not like well preserved in the point cloud prediction result from the baseline model. but we don't really care those things a lot. We mostly just care about foreground objects. In at least we care them more than the background, right? So that's kind of decent. And then we kind of ran some more demos here. So here we're not just predicting the point cloud, we're also run some detector on top of the predicted point cloud to see how we can do it for the downstream, right? So here you see these green boxes, which is detected objects on top of our predicted point cloud, and the yellow ones are ground truths. So basically you get from the human annotation. And then what we want to see is that if the detected objects matches with the ground truth objects in the predicted point cloud, right? So if you look at this demo, I think they are pretty aligned. So we see a lot of these kind of results in our demo. As long as the object come into the scene, come into the point cloud that we predict, we can kind of capture those blobs by the detector and then get some reasonable box out of it. And then after detection, we do tracking. So here we didn't show the ground truth, but just kind of associate the detection we have across time. It's not straightforward to visualize the ground truth because we use color specific encoding here for each box, right? So if we add ground truth problem, we have to use a unique color. But anyway, so you'll see these kind of boxes, especially their identities are consistent over time as long as they are kind of captured in the predict point clouds. Okay. So that's the result from the baseline. So what are the limitations of the current method, right? So once we kind of develop this pipeline, we're thinking about the most straightforward thing is that the point cloud we predict from this baseline model, they didn't look real, right? So you see all of these kind of blurry predicted shapes on the point cloud, either the foreground and the object, foreground object and background scene, right? The foreground object, the car doesn't look like a car; it's kind of like a blob, and the background thing, sometimes the model just ignore about it, right? And then the other thing is that the current model kind of only capture the big things, the object with large shape like cars, the vehicles, but not the small things like pedestrian, like traffic cones, those kind of very like objects with fewer Lambda points. So they kind of ignore it to some extent. For example, if you see this demo on the right, there are some pedestrians moving in the scene, and then the model just kind of ignored them because we basically we can't predict any motion of these points for them. Okay. So to kind of solve this problem, or to solve this problem to some extent, we are developing some newer algorithm, which we call learning fine-grained point cloud prediction with pyramid LSTM or pyramid ConvLSTM. Okay, so if we kind of just think about this problem, maybe the simplest hypothesis to this problem is that we are compressing the hidden representation too much, right? Like I said before, we're just using one-dimensional feature to represent everything, like every single point in the 3D world. Like even they have just 150,000 of points. We're just using this 500 and 112 dimensional feature to represent everything, which might not be possible. So that's why the model kind of just ignores small things, but only preserve large objects with large shapes, right? So to kind of solve that problem, we just try some straightforward solution first, which is kind of obvious. We just replace the one-dimensional feature to the heat map, right? To kind of represent or reserve this kind of spatial information. So to kind of adapt to that, we also change that fully connected LSTM to convolutional LSTM, which is very standard approach in the community. And then we also kind of add this kind of escape connection and upgrade the encoder decoder for the range-based method, right? So we're not just using some like 2 or 3 layers of convolution. We're using more like people have handcrafted like well-known backbones with very strong performance on similar tasks. For example, the Darklet 53, right, which is kind of a good model people use for point cloud segmentation, but we're kind of borrow the backbone here to do this point cloud encoding. And once we do that, some weird thing happens. First, one is that the training doesn't converge very well, right? So basically, the model doesn't, like, even sometimes performs worse than the baseline model. Right? If you think about it, we just kind of change this encoder and then change this output representation to the hay map, and inside the encoder we change the LSTM, and then we also change the decoder to darklet. So I think everything is normal, but it seems like there's some problem. Later we kind of revisit this and we find, okay, maybe it's this feature synchronization issue, right? So if you think about this architecture, like at every frame after this convolutional LSTM, so the feature, the hidden representation, all of it is kind of being propagated temporally into the next time step, right? So it's kind of feature at t = 2 for feature at this arrow. But when we do the skip connection from the encoder to the decoder, they are like just copying the feature, right? So there isn't any temporal modeling. So you can think of this feature as still at t = 1, right? It's still at the input time step, which is kind of not synchronized with this feature you use here as the start of the decoder, right? So that's the one of the problem we have found so far. So to deal with that, we kind of just do this symbol adaptation. So here we just call this method spatial hierarchical LSTM, which is kind of reasonable because we are using multiple hierarchy to learn the features, even though inside this skip connection. So what that means is that we also have this convolutional LSTM for this higher level feature, the last layer of feature from the encoder. But in the meantime, when we do skip connection from encoder to decoder, we're also adding some LSTM here, right? So that we can make the temporal or the time step for each feature consistent, right? So that means we kind of add this the green arrow here, and also inside the green arrow we have this another convolutional LSTM which doesn't share with this first convolutional LSTM. And similarly, when we do another skip connection, we just add another convolutional LSTM, and then we just add them through time or propagate the feature through time. So this is kind of simple adaptation we have on this model, but the result is kind of surprising. Is that first of all, the training converges quite stably, which is reasonable. And the other thing is that we've seen a very large boost in terms of performance on all of the metrics. So sometimes some metrics, this is on average 3 by 8 times. Some metrics even kind of have 10 times improvement. So that's kind of good. And we visualize again the results here. On the left, you see these results from baseline. On the right, you see results from this neural model. And to make the visualization a little bit more clear, we color each point in both ground truth and predicted point cloud. So basically, each color represents the error, like how big error of this point correspond to the actual point location it should be, right? So the red dots, the red point means that this point has a large error, and the CM means that it has lower error. And the reason that we also have error in ground truth is because of this chamfer distance, right? So you also compute each point in the ground truth if this point can find a matched point in the predicted point cloud, and their distance, how big the distance of this matching is, right? So the best result you can have, or the ideal result you can have, is that on both ground truth and predicted point cloud, you have everything in CN and not a single point in red. But that's not the case in the results. But overall, if you compare this parameter LSTM and the baseline we have SPFNet, is that we see much less red points in the prediction, and also in the same time, the structure of the background is much more, it's sharper, right? So you see more details in the background. And also for the foreground object, you see kind of clear shape of the vehicles. So that's are all good signs. And similarly, we kind of visualize the results on scenes with pedestrians moving. So on the left, you don't see any pedestrian predicted moving on this prediction, but on the right, for this neural model, you see there's some pedestrian predicted are moving here. Similarly here, So we can kind of capture this small motion for either pedestrian or other background objects. Okay, sounds good. By the way, if there are any question, we can address in kind of throughout the talk. Otherwise, I'm going to cover the last part of this talk.
Perfect.
Okay. So nothing I want to talk about or we're trying to advocate in recently is these new data sets. So one of the reasons we're developing it is we want to benchmark, we want to use it to benchmark sequential point cloud forecasting in this new task in a more rigorous way. So we developed this data set called all-in-one drives. So basically we want to have everything inside it. So that's what we call it all-in-one. So it's a perception data set only used for, or mainly used for autonomous driving. And it has some unique feature like high density long-range point cloud we will introduce later. Okay, like I said, one of the motivation we want to build this data set is we want to benchmark or make the first change on sequential point cloud forecasting. And we are building this data set with Carla, which is a simulator, right? So it has a good and the bad things of building a data set with simulator. So the good thing is that this simulator is very high fidelity. It's the state-of-the-art simulator, one of the simulator many people are using right now. And it's very easy for closed loop planning evaluation, right? Because it's a simulator, you can just run your planner inside it. So the reason we have is with Color is that we are thinking, okay, we have this point cloud forecasting and we have the downstream, we have all of the annotations. So then once we build our perception prediction pipeline, we can fit into planner and run closed loop evaluation in a very kind of like seamless manner. So that's good thing. And bad thing is that whenever people use simulator to generate data sets, there's always reviewers saying that, okay, the reality, the gap between the real world and the simulator, right? So that's also reasonable and kind of a downside, but we kind of believe in the future the domain adaptation and some like similar techniques can kind of address that problem to some extent. So we're still deciding to use Karna. Another good thing from Karna is that it's very easy to get all of the annotations, right? So as long as you kind of be familiar with Karna, can process everything out of it and generate any kind of annotation you want. So to that sense, we have all annotation. We have annotation for all mainstream perception tasks. So anything you can imagine, like point cloud segmentation, image segmentation, right? Detection, tracking, forecasting, like velocity estimation, and etc. So so it's kind of useful because sometimes people want to do multitask learning, and then you need multiple sources of annotation, which we all provide. And on the other hand, we also have a very comprehensive sensor modality. So this the major thing come from Karna itself, right? So inside Karna you have LiDAR, you have image, so you can get depth and RGB images, and you also have radar. Although I think radar right now is still in the prototype, but in the meantime, we also like using based on Karna API, we kind of simulate SPAD LiDAR, which is kind of something new. I don't think there's other datasets, other popular driving datasets that include many other sensors also include SPAD. I think there are maybe one or two datasets only have SPAD, but in the popular one, the Waymo new things, I don't think they have SPAD. In the diverse environmental variations, we have a lot of distribution data like car crash and off-road driving, right? And violation of traffic. You can just run over to the red light and and hit a pedestrian, for example. So so all of the things are having inside inside our data set, but it's kind of defined by our rules, like how aggressive each vehicle should be. And then we kind of make that like defined in advance so that you can generate this out of distribution data. But most of the data are still like in the distribution, so it kind of matches with the real world. You don't have car crash, a lot of car crash in real world, right? So yeah, so that's kind of the main feature of these data sets. And yeah, so here is just a little bit more details. We have every sensors. We introduced like stereo depth LiDAR, radar, SPAD LiDAR, MU GPS, and all 360 degree. And we have different density of LiDAR. So this is something probably only possible in simulator at this moment, right? So in real world LiDAR, I mean, there are some dense LiDAR nowadays, but it's not that dense as what we can get in simulator, right? So you can get something like 4 million or 1 million points LiDAR for a single frame, so that you can kind of develop long range perception algorithm like detection, right? So nowadays, like most of the data, LiDAR data people are using, probably this 100K or 200K. So you only can detect object like less than 200 meters. Sometimes even it's less than 100 meters, right? And then we also have SPAD. And on the other hand, for the annotation, we support both scene level and object level annotations. For scene level, we mean like this video, semantic instance, and parametrics computation. So either in images and point cloud. So we have sequence of these data for it. You can use it for a range of perception tasks. And then also we have maps. So this is pre-built with Carla. And also there are some open source map people have built external to Carla, but there are many maps and we know everything inside it, right? So which lane is which, and where is the traffic light signal, and etc. So basically, you know every structure of it. And for the object level annotations, we kind of have all of these boxes, either in 2D space and 3D space, and the identity. So basically, you have trajectories, and also we have object class, vehicle models, motion log, right? So you have velocity at each time step for every object, right? So that's kind of useful when you do trajectory prediction or you do planar and etc. And we also have the control signal. Okay. So here, I think this concludes our talk. I see there's one thing in the chat, but yeah. Okay, so I think this concludes our talk here today. So here the take-home message is that there are a lot of innovation nowadays, but we kind of want to let the community know that innovation is not only possible to happen at the module level, but also at the pipeline level, right? We can kind of do different combination or different order of the pipeline in the autonomous driving, right? We can also kind of demonstrate that the simple SPFNet baseline can preserve information for large objects, but sometimes it knows details, especially for small objects, right? And the next thing is that we have this pyramid LSTM that increases the details on global structure and also small object in the same time. So that's pretty good. We kind of see a large boost in terms of point cloud forecasting performance. And then we also have these new all-in-one drive datasets. Actually, we already make the datasets available to download publicly. So it's on our website, aodrive.org. So it's kind of a large dataset where we want to use it to benchmark a lot of tasks. But yeah, I think the change will be online soon. Yeah. So that's it. Thank you for listening. Thanks, everyone.
Thank you for the talk, Xinshuo. Do we have any questions? I had a question relating the point cloud density and the point cloud forecasting paper that you presented before. So for point cloud forecasting, would it be possible to have forecast from a sparse cloud onto a dense cloud? Because currently they are the same density, and I was wondering if there is a possibility to increase the resolution of the point cloud temporally.
So I think first of all, the current point cloud we are forecasting is already quite dense. So the LiDAR we use is from VLAN 64. It's quite dense, especially within 100 meters. But beyond that, it's probably sparse. If we go even denser, then I think the main difficulty is the model design, right? So how do you process all of those points? I think right now in the, let's say, point cloud processing community, there are tons of, let's say, graph neural network based point cloud processor and some other types of point cloud processor. I think if you come with a very large point cloud, then it's not efficient to do it, right? Because you have to do these neighborhoods, like all of these assignment and the neighborhood or clustering and etc. So I think it will like very memory insufficient, memory inefficient, and also the speed is not going to be reasonable, I think, too.
Yeah, definitely. I mean, the question was, to give you a more applied context, the question was motivated by using cheap LiDARs. For example, we are on BLP 16 or 32, and we expect to see a more dense cloud or reconstruct a more dense cloud in the future. So this was the motivation behind the question.
I see. So you're asking if you are feeding to a sparse LiDAR input, you want to get a dense output?
Exactly. Yeah.
Yeah, I think that's definitely possible, right? Because when you, I mean, the simplest thing you can do is just to do temporal point cloud aggregation, right? I think, for example, in the new things, people are doing that, and I think in a lot of industry, people are doing that, right? You just aggregate, let's say, 5 or 10 frames of point cloud into a single one and do detection. But that's kind of more like hand design, or it's like pre-processing, right? But here, if you do some temporal learning, I think you will do better. That's probably a different task to this, right? So you're not, I mean, you can also do the forecasting in the same time, but you cannot do it. You can also do not do forecasting, right? You can also just do, let's say, temporal aggregation to get denser point cloud, right? So if you do that, it's a different task. You have to change the point cloud, sorry, the problem formulation a little bit. Yeah, I think there are some works are doing point cloud interpolation, but not this kind of learning-based aggregation. Yeah, that's an interesting thing to try, I think.
I see. Thank you. Yeah. Do we have any more questions? So let's thank Xinshuo. Thank you very much for your presentation. And
yeah, thank you.
So I think we have the next